So last session we studied functions, like what is injective function, and then surjective and then bijective functions, and then we also looked at relations a bit, which today I will go over again. You can follow with the book, which is posted in the important channel. You can download the book and follow along with the book, since we are following the book. So, is there any questions anyone has about these topics today? I will first have a review. Okay, so let's start with a review of equivalence relations. So basically, a equivalence relation is a relation. So equivalence relation. Let me write it fully. Equivalence relation. Equivalence relation is a relation on a set. Let's call this set, suppose A. Equivalence relation is a relation on set A that satisfies these following properties. So the first property is reflexivity. This just means that given any element of this set, this element is in relation with itself. So let's denote this equivalence relation by tilde. So this symbol, for example, you can use any symbol. This can work for now. So firstly, we have X is in relation with itself for all X in this set. So that's the first property, that you are always, any element is always in relation with itself. And then the second property we have is the symmetry, which just means that if you have two elements, let's say X and Y, and if X is in relation with Y, this implies that Y is in relation with X for all XY in the set A. So that's the second property, that's symmetry. And then we have the third property, which is transitivity. So this basically says that if X is relation with, say, Y, and Y is relation with, suppose, Z, then we have X is in relation with Z. So this basically means that if, say, X is related to Y and Y is related to Z, then X is also related to Z. It's kind of like that. So this is true for all x, y, z in A. Now let's have some examples of equivalence relations. So a very simple example is the equality relation. So the equality relation example, equality relation, actually we just call it equality. This is denoted by this equal sign, as we all know, on the set of real numbers. So this is R. So the equality on the set of real numbers is an equivalence relation. So let's look at why. So firstly, it satisfies the reflexivity. It does satisfy reflexivity because if you take any number A, say a real number A, if you take real number A, then we always have A is equal to A. This is always true. So reflexivity is done. We have the reflexivity, then we also have symmetry here. Because if you have, say, A and B real numbers, for this you also have A equals B. This also means that B is equal to A. For example, let's say 2 is equal to 2. This is, if you flip it, it's going to be the same. Kind of like that. And then we also have transitivity. Say you have A, B, C in the real numbers, and you have A equals to C, A equals to B, and B equals to C. Well, by just substituting this into this equation, you can see that A is equal to C. So it satisfies all these three properties, so it's a equivalence relation. Is there any questions so far about this? Okay, so let's look at another example. So this is the second example. So we can actually have a new definition of an equivalence relation. So for example, you can take, say, 2 points. Say you take 2 points of the graph of the plane of the 2D plane. Say you pick x and y from R2. R2 basically just means that it's a two-dimensional graph basically. So you have x and y axis here. This plane is called the R2, or the two-dimensional thing. So if you take some point, let's actually take 2 points actually. Take this coordinate and some another coordinate from R2. Now we can actually define these points to be equal with an equivalence relation. So the equivalence relation that we can use here is that, say define these 2 points to be equal points equal if y0 minus x0 square is equal to y1 minus x1 square. So you can define these points to be equal like that. It can be very arbitrary, but you can this equality here. This is an equivalence relation because firstly uh, we have reflexivity. We have reflexivity already because let's just consider this point x0 and y0. So x0, y0 is in relation with itself. So say let's consider, let's put this sign for the equivalence relation, denote tilde to show equality. Okay, so now we take this point and now we just relate it to itself, which just means that we use this as our definition that we as we define the points to be equal. So let's just plug in these values now. So basically for we replace the x0 and x1 all together. So firstly we already have this one by substituting the values, and then for the second point, the second point is the same point we have here. So you can just write the same thing. So it seems it already satisfies reflexivity. So this is done. And then we also have symmetry because if you take this equation and flip it, let's take it here. If you take this equation, this also means the same thing if you wrote it the other way around. Agree? You guys agree on this? And then symmetry is done. And then we also have transitivity. This one is requires a bit more step. This equation we basically, can you explain the same equation? Okay, so this equation is basically, we just came up with this equation randomly to say that 2 points are equal if it satisfies this equation. It's completely arbitrary. It's just a definition we picked to show that 2 points are equal. So our claim is that this equation on those 2 points on this set is an equivalence relation. So it already satisfies reflexivity because if you take this point and then take the next point to be the same as this point, these 2 points are already equal. That's why it satisfies reflexivity. Now it also satisfies symmetry. Let me actually remove this stuff to reduce some confusion to show the relevant. Okay. So it also satisfies symmetry because if you take this equation and flip it, it just means the same thing. Did you get it? And then we also have transitivity. So now we take 3 points. We take x0, y0, x1, y1, and then x2, y2. We take 3 points. So let's first set these two equal. So that would mean y0 minus x0 square equals to y1 minus x1 square. So it's the equality of these two. Now let's do the equality of these two. So that would be y1 minus x1 square is equal to y2 minus x2 square. So already you can see that these two equations are definitely equal. These two equations are the same thing. So you can see that all of this implies that y0 minus x0 square is same as y2 minus x0 square, x2 square. So this just means that x0, y0, and x2, y2 are equal. That's it. It's that simple to show equivalence relations. Okay. So that's done transitivity. So this equation is an equivalence relation for this. Yes, we can define arbitrary relations like that. You can also you can also do it geometrically. In the end, if you want them to be equal, your definition just has to satisfy the equivalence relation. Any type of equality has relation kind of connects to an equivalence relation. So yeah. So that's equivalence relations. The next thing we have is an ordered relation. We have an ordered relation. That's the next thing we have. So an ordered relation, this is denoted with this less than symbol on a set. Let's say the set is A. That satisfies these following things. So the first thing is comparability. The first thing is comparability. So if you take x and y from this set A, so for every xy, in A, either x is less than y or y is less than x. Either one of these will hold. So that's the first condition for an ordered relation. The second condition we have is non-reflexivity. Non-reflexivity. So this is the second condition. So this second condition basically says that x less than x is never possible. Basically, it's the opposite of reflexivity. And then the third condition we have is transitivity. Yeah, it's here again. So x less than y and y less than z implies that x less than z for all x, y, z in A. So that's an ordered relation. So a very simple example, the best example of an ordered relation is ordered relation uh, on the real numbers. This should be simple enough to understand. The best example actually, because if you have, for example, 2 is less than 3, but so for comparability, 2 is less than 3, but 3 is not less than 2. We just put this kind of cutting mark to show that it's not less than 2. So 3 is not less than 2. And the next thing we have is, let's say any number 1. 1 is not less than itself. So that's an example. It already satisfies that. And for transitivity, say 5 is less than 8, and say 8 is less than 10, then 5 is also less than 10. So that's an example of an ordered relation. It's pretty simple. Now, if we have, we also use this specific notation here to show less than or equal to. This just means either, let's say A less than equal to B, either A equal B or A less than B. This, it satisfies this ordered relation. So that's ordered relation for you. Now we have a few more things about ordered relations. We have the open interval, denoted like this, a like written like this pair. So this is the set of all x such that a less than x less than b. So this is an open interval. That's how it's defined using the order relation. Now, if this set is empty, if this set is empty, then a is the immediate predecessor of x. I mean b of b. A is the immediate predecessor of b, and b is the immediate successor, and b is the immediate successor of a. So this kind of means that if you have, say, for example, you have two numbers here. Let's say this is number 2 and then 3. This set basically means the set of all numbers between a and b. And if you have no numbers in between, then 3 is called the immediate successor of a. I mean 2. You can also say successor of 2. That's fine. You don't need to say immediate. 3 is successor of 2, and 2 is the predecessor of 3. So that's the open interval. Sorry about that. Now we have, if we have two ordered relations, say, okay, we say two ordered relations are of same order type if there is a bijective correspondence between them that preserves order. So basically, are there cases where an open interval is the empty set? Yeah, the open interval is an empty set in the case of natural numbers or the positive integers or any integer, because there are no. Let me show an example here. So here, let's say this is from the set of integers, okay? This is in the set of integers. Now we want to say the open interval 2 and 3. Is there any number between 2 and 3 for the integers? There isn't. So this is empty.
Wait, do you
Typhon,
mind
did you want to?
explaining the two th three integer open interval set?
Yeah, I just explained it.
Oh,
Basically,
I see. So it's in the integers. Okay, my
yeah,
bad.
yeah, that's it. So basically, if you have two sets A, B, two sets A and B with two ordered relations, let's say this symbol and A, and then this one and B. These are said to be the same order type if there is a bijective correspondence between that preserves order. So this is like, let's say we pick A1 and A2. Let's say we pick A1, A2 from the set A, and then we have A1 and this ordered relation less than A that is defined on this set A, A2. If this implies the function that after applying satisfies this ordered relation less than B. So this function is definitely going to map from A to B, a bijective function. So this is what is meant by order preserving bijective correspondence. So let's look at an example. Let's consider the open interval 1 to 1. Let's consider a function from this open interval to the real numbers. Of course, this has the ordered relation less than, and these two sets actually have the same ordered relation. So of course they have the same. So let's say this function is defined as like this. So we want to show this set A and this set B have the same ordered relation. Now we really just need to take this function is bijective first. So if this function is bijective and then it satisfies the ordered relation, then these two sets have the same order type. So this function is bijective. I won't go over why it's bijective. You can check that for yourself. It will be a good exercise. So this function is a bijective. Now let's, for example, pick any. Let's say we pick a1 from and a2 from this interval. So this just means that a1 and a2 is between these numbers -1 to 1. So we pick these two numbers such that one is less than the other. One is less than the other. Now let's denote this with a, this relation. Now if we take f of a1, we have a1 by 1 minus a1 square. And if we take a2, this is a2 by 1 minus a2 square. So which one is bigger? Which one is bigger here? Of course, a2 is bigger here. A2 is bigger here. This one is bigger. So we can say if a1 is then b, which we said on this, which we call the real numbers, and if a2. So it preserves the order. So we just showed that if you have two same sets, then they have the same order type, or if you have subsets of real numbers. So that's an example. So that was the, you can see more examples in the book. I will go over bounded sets now. Is there any questions so far about this? Okay, so why are less than sub A and less than sub B symbols are used? So I use these symbols to show that the set A has the ordered relation less than sub A, and the set B has the ordered relation less than sub B. They have two ordered relations that we denote by a different symbol to show that they are different, to distinguish between them. But actually, these two are the same ordered relation. These two are the same here in this case. Is that clear? Okay. Yeah. The order. Would we say the order relation is anti-symmetry for greater than and less than relations? Yeah. You can say that. So means, so A greater than B means not A less than B. So it's the opposite. As I said before, if it doesn't satisfy this comparability, then you can also write x is greater than y. You can also write x is greater than y here instead of using this symbol. So now we can talk about bounded sets. Now we can talk about bounded sets. So we say that a subset A of, let's say we have a subset A0 of, let's say, a set A. Let's just use something else than A here today. Let's say A0. Actually, let's just use A. No problem. I'm just bored using A everywhere. Subset A0 of A, and A is an ordered set. Ordered set. A is an ordered set. We say a subset A0 of A is bounded if it has an upper bound or a lower bound. And a lower bound. So let me show what's an upper bound. So basically, set let's just say A0 is bounded above if we have some element if we have some element that is, say, x, that belongs to a parent set, that is A, such that x will be greater than all A in this set. So that's an upper bound. It basically means if you have this set here, for example, this is the interval, or it can be any set. I'm just drawing for visualization. Let's say this part is the subset A0, and this entire thing is the set A. If you have some x in this set A and then some A in this set A0, then x is an upper bound. We say x is an upper bound. So we say x is an upper bound, and this set is bounded above. So whenever there is an upper bound, we have the set is bounded above. So similarly, you can say bounded below if, say, x is greater than all a. So let me show the next diagram here. So let's say this is x here and this is the set a0, and we have some a here. My bad, I used. If x is less than all a, if x is less than or equal to all a from for all a in a0, then this set is bounded below and x is a lower bound. So that's what upper bounds and lower bounds are. Then similarly, we have, since there can be any upper bound, the upper bound also doesn't necessarily have to be in the set, in the subset itself. It just needs to be in the parent set. So if we take the set of all upper bounds, there will be a least upper bound. So we write sup A, which means the supremum of A. So this is supremum of A, gives the least upper bound. Gives it, let me just, I wrote A but it should be A0. So sup A0 gives the least upper bound for A0. Yeah, sup. So sup gives the least upper bound for A0. This just means that if you take the set of all upper bounds, say there are more upper bounds, say Y here or whatever, B, U, whatever. If you take the set of all these upper bounds, you take the set of all these upper bounds, the smallest upper bound, you take that one, that's going to be the supremum of A0, supremum of that set. So that's what the least upper bound means. We just say supremum and least upper bound, they mean the same thing. So whenever you hear about supremum, just think about least upper bound. We will be sticking to least upper bound for in this series, I think. And then we also have the infimum. So this means the infimum of A0. Infimum A0. So this gives us the greatest lower bound. Basically, if you take all the lower bounds and the largest lower bound, this will give you that for A0. No, the supremum is not a set. The supremum is not a set. Let me give an example, some concrete example. Example. Take this open interval. Let's say 0 to 1 from the real line. If we take the supremum of this subset, we get 1, because 1 is the number that's greater than all elements in this set. 1 is the number that is greater than all elements in this set, and it's also the smallest number that's greater than 1 here, because in the open interval we are excluding 1. So the supremum is 1, and the infimum is 0. Yeah, it doesn't necessarily have to be in the set itself. So as you can see, 1 belongs to the real number. And as I showed in this example, that an upper bound For the upper bound, we take the elements from the parent set, not the subset. As you can see, here we wrote x belonging to A, and yeah, that's the example of supremum and infimum. Any questions about this? Do you guys need more examples? I think no questions so far. I will continue now. So far I have been going over definitions and examples, but there is very important theorems that I left over. And before moving to them, I think we should take a 5 minutes break. What do you say, Saison? After the 5 minutes break, we can come back. Give it some time to process all of this. I need to drink water. Okay, guys, we are back after the 5 minutes break. Now we will go over the theorems that we missed. So we will first go over the theorems. Actually, let's go over the theorems for this least upper bound stuff. So first we need a definition. A set A has the least upper bound property if for every non-empty subset for every non-empty subset, say A0 of A that is bounded above least upper bound property has a least upper bound. So what this basically means is that if you take every set, let's say this is A, if you go back to this example, if you take more A0s of this set, like all subsets of this set, all non-empty subset that is bounded above, that has a upper bound. If you take all of these and they all have a least upper bound, then this set A, it is said to have the least upper bound property. Then similarly, it has the greatest lower bound property. Greatest lower bound property. That is right bound here. Greatest lower bound property if non-empty subset A of A that is bounded below has a least, I mean greatest lower bound, greatest lower bound. So that's our definition. So now we immediately have a theorem to prove after this. That is, let A be an ordered set. So what we are going to show in that, what we are going to show, yeah, sorry about the noise. It's really noisy here. Sorry about that. Okay, let A be an ordered set. So what we want to show is that if this set has the least upper bound property, then this set also has the greatest lower bound property. So that's what we want to show. So if this set, if A has LUB property, meaning least upper bound property, then it has GLB property, greatest lower bound property, GLP property. So we need to prove this now. So firstly, we actually have two directions to prove here. It should have been an if and only if, but let's just keep it simple for now. So let A be an ordered set. Ordered set with the least upper bound property. So firstly, let B be a non-empty subset. Non-empty subset that is bounded below. So basically our strategy is that we pick the non-empty subset of A that is bounded below. Then we consider the set of all lower bounds, and then we consider the set of all lower bounds, and we pick the upper bound for that lower bounds, the set of all lower bounds. We pick the largest one. We are basically going to show that the least upper bound and greatest lower bound, they can lead to the same type of set structure. It's the same type of structure. So that's what this theorem is saying, and we can prove it that way. So consider the set of all lower bounds that is given by A set of all x in A such that x is a lower bound of B. So consider this set. Now we have B is bounded below. So this set is non-empty because there are lower bounds of B because B is bounded below. So this set is non-empty. A is non-empty. Let's just say it's not equal to empty set. Then the next thing we have, if you notice, since each element is a of each since each element of L is a lower bound of B, every element of B is a lower bound for L. If sets A and B have same elements, but A is ordered by relation greater than and B is ordered, then would their infimum and supremum be opposite? Yeah. That's also an alternative way to prove this. We can consider two different orders and show that the supremum leads to an infimum and the infimum leads to a supremum. If the relations are ordered relations are just opposite. So now every element of B is an upper bound for L. So this shows us that L is bounded above. And now guess what we can do? L is bounded above, so it has a least upper bound. So L has since L is bounded above, L has a least upper bound. It has a least upper bound. Let's call it A, or let's call it alpha actually. It has a least upper bound in A. Now, since alpha is an upper bound of L, it means that alpha is greater than all elements in L. Are you guys able to follow this so far? So take any L from this big L, then this L is at most alpha, at most alpha. So now the thing is, remember that L is a B is a upper bound for L. So let me draw a picture here. So let's say this is the set B, this is the set B, and then L is the set of all lower bounds. So let's say, for example, this is L, and alpha is somewhere here. Doesn't this mean that this means that the greatest lower bound of B is alpha? So we can say that supremum of L is equal to the infimum of B. What does this show? Here B was any arbitrary non-empty subset of A that is bounded below. Doesn't this look like the definition of greatest lower bound property? So then A has the greatest lower bound property. And then we are done with the proof. So a pretty neat proof. It's pretty clean. Any questions about this so far? Just yes or Aurelius. I guess there's no questions. So now let's go to the another proof now. First we will define a partition.
We have a question saying to summarize the proof.
Oh, okay. So basically the theorem says that if an ordered set has the least upper bound property, then it also has the greatest lower bound property. So here's how we did our proof. So first we defined the set A to be an ordered set with the least upper bound property. Then we picked any non-empty subset that is bounded below. We call that B. We picked a non-empty subset that is bounded below, a non-empty subset of A that is bounded below. Then we picked the set of all lower bounds of B. So this is the set of all lower bounds of B. Lower bounds of B. This is the set of all lower bounds for B. And this set is non-empty because B is bounded below. So this set is non-empty since P is bounded below. Then every element of B is an upper bound for L. So L is bounded above because if you notice, the elements of L is less than B, and then elements of B is greater than L. You can see in this picture here. So L is bounded above. Since L is bounded above, it has a least upper bound. Let's call it alpha. That's in this set A. Then you pick any L in this big L. Then this little L is at most alpha. So this says that any element of L is at most alpha. It's not more than that. And now notice that L is the set of all lower bounds. Is the set of all lower bounds of B. So and L is at most alpha. This shows us that greatest lower bound of B is alpha because this is the greatest L can reach. So supremum of L is infimum of B. And here B was an arbitrary non-empty subset of A that is bounded below. So this shows that A satisfies the greatest lower bound property by definition, since this just matches the definition. Is that clear? Okay, here. Now we will move on to something very important. That is, first I will state a theorem about equivalence relations here. Actually, I did that the past lecture, so I'm gonna do now. Now we will start on the integers. So we will start on integers and real numbers now. So before defining integers and real numbers, we need to understand what are numbers. And before that, we need to define what you call a binary operation. So a binary operation is a function, the function f that has the Cartesian product of E and A. So a binary operation on a set A. On a set A is a function that takes the Cartesian product of A with it itself, mapping to A, denoted by A F B for this pair AB in this Cartesian product. So that's what binary operation is. For example, addition is a binary operation. Because if you take A plus B, you're essentially taking some A and B, this pair from the real number with itself. So that's basically what a binary operation is. Now using this, we will define what you call a field. So fields are basically the what you call it, is the groundwork for building many types of numbers actually. So the real numbers is a field, the rational numbers is a field, the complex numbers is a field. So let's define any number Yeah, field is an algebraic structure. Yeah. So a field is a set F with two binary operations, addition and multiplication. I will denote multiplication by this dot with the following properties. Also, in the binary operation on the set, wherever you apply that operation, it will stay in the set. In here, if you add two numbers from the real numbers using this binary operation, then the result will also be in that set. Just making sure, because I won't be defining closure here. Okay. So the first thing we have is the commutativity of addition. This is basically, if you take a plus b, it is same as saying b plus a for any a and b in this field. And then we have the associativity of addition. This basically says that if you add the number and before adding it to the other number, you group the numbers together. In this case, b and c. This is same as grouping the first two and adding the third number for any a, b, c in F. And the third thing we have is the existence of an additive identity. You also call this the zero element. So you denote that element by, of course, writing zero. And then you have the additive inverse. So it's denoted with negative a. You put the minus sign and then write it like this. So this will give you the additive identity. So applying the additive inverse gives you the additive identity. So there needs to be some additive inverse in this field. So these are the addition axioms. Addition axioms. And the next things you have is the multiplication axioms, which are pretty much same. So a multiplied by b is same as b multiplied by a for all a b in F. And then you also have associativity. Associativity. So if you multiply b and c first and then multiply with a, this is same as multiplying a with b first, then with c for a, b, c in F. And then the next thing you have is multiplicative identity, which is the what we call 1. So it's denoted 1, and this will just give you the number A. So any identity is basically, if you apply the operation, it will just stay the same. And then lastly, we have the multiplicative inverse. So this is denoted with A, and you put the -1 in the subscript, and this gives you the multiplicative identity. So A inverse 1. So these are the what you call the field axioms, and these are the multiplication axioms. Overall, if combining all of this, you have a field. So an example of a field is rational numbers or the complex numbers. But the next thing we have is an ordered field, that is simply a field with, since we said a field is a set with two binary operations, we can, an ordered field is basically just a field with an ordered relation. Field with ordered relation satisfying. So an ordered field basically allows you to compare two numbers. So the first thing we have is, we call this trichotomy law. So this says that either for every A in F, we have either A is greater than 0, meaning A is positive, or A is negative, or A is equal to 0. So either one of these will hold. So this is the trichotomy law. Then the next thing we have is the addition property, which says that if A is greater than B, then A plus C is greater than B plus C, where C is any constant you add to both sides. And then we have the multiplication property, so multiplication property is basically, if A is positive and B is positive, then if you multiply these two, you get a positive number. So this property here, it forces us to say that the product of two negative numbers will be positive. So that's what an ordered field is. Now the real numbers, R is an ordered field. R is an ordered field with some extra properties. Can anyone tell me what's the first property that I did not mention here that R has? Anyone, any idea? That all also solutions like electricity. Okay, so R has the least upper bound property. R has the least upper bound property. And another property that if A is less than say B, then there is some C such that A is less than C less than B, meaning that you can always find some number between given any two numbers in the real numbers. So with these two properties, R is called what you say complete ordered field. So because of these two extra properties, R is called complete. So that's the complete ordered field. There are some a lot of interesting facts now you can prove about the real numbers. For example, the first thing you can prove is, let's say, a theorem. This is very important. 0 times A is equal to 0 for all A in R, or let's say F. So this is a very interesting result because we did not state anywhere in the axioms that if you multiply something with 0 that you get 0. So this is something you have to prove. That's quite funny, to be honest. So does anyone have any idea how we can prove this? I think just sir knows how to prove it. Write 0 plus 0 times A, expand using B plus C times A. Okay, let's see. Let's apply just sir's idea here. So 0A is same as writing 0 plus 0 A, but there is one issue here. We need to make sure that 0 is unique, but it will work, I think. And expand using B plus C. So by associativity, we can say 0A plus 0A. Then we have 0A is equal to 0A plus 0A. That's pretty neat. Then what do we do? we should add the inverse of 0a. Correct. So since 0 is some number, we are actually multiplying this, and it's a number that we have in this field. So we can add to both sides 0 times a. We add the additive inverse. So basically we add the additive inverse here because you can see it's 0. The only way to get that 0 is somehow by adding the additive inverse. So in the left side we are left with 0, and the right side we have 0a is equal to 0a. This just means that 0. So that's proved. Nice job. I stole this neat idea from Spivak as well. Yeah, Spivak is really nice. Okay, so you guys can do the rest of the proofs that are very similar. You can check the book for the rest of the contents. Now we will go over the important facts that we will need. Okay, so now we will define the integers. Before defining the integers, we will define an inductive set. So a subset A of R is inductive if it contains the number one, and if for every x in A, x plus 1 is also in A. So this is what an inductive set definition is. So basically, let's say we start with the set 1. We start with the set 1, and if for every x in A, x plus 1 is also in A. So then we get 2, and because this is also some x in A, then we get 3. Actually, yeah. So this is an inductive set. Is it? Does this satisfy the definition? Yeah, that's not inductive. So basically, in inductive set, you get something like this. It starts from 1, 2, 3, and goes on forever. But this is not necessarily the set of integers. So that's basically what an inductive set is. Now, using this, we can now define the set of positive integers now. So first, let A be the collection of all inductive subsets of R. So let this curly A be the collection of all inductive subsets of R. Then the set of positive integers, we write this as Z, and then we add a plus on the subscript. The set of positive integers is the intersection, and we pick any element from this collection. So this collection is acting as an what you call an index set here. So Z is the intersection of all inductive subsets of R. This is how we are defining Z, the positive integer Z plus here. So I'll just call this set of positive integers. So now we have, following from the definition, we have two properties of R. I mean, two properties of the Z plus. The first property is Z plus is inductive. So this is inductive. The second property is, this is what you call the principle of induction, or mathematical principle, or principle of mathematical induction. So this states that if A is an inductive set of Z, set of Z plus, then A is equal to Z plus. So these are the two properties of Z plus that we have right away. So I will prove this in a bit. And then what we also have another definition. So this is what you call a section. Section of positive integers. Section of positive integers. So this is the set of all elements that are less than, say, n plus 1. So this just goes from 1 to n. So this is a subset of the integers, positive integers. Yeah, so this is called a section. Now, we have a very important theorem about the integers. That is, we call this the well ordering principle. This is the well ordering principle. So this states that every non-empty subset of Z, I mean Z plus, every non-empty subset of the set of positive integers set of positive integers has a smallest element. Now we can use quote-unquote induction to prove this. So in here we can use this property, that is the principle of induction, to prove this well-ordering principle. So before proving this, I think we need a lemma first to help us. So firstly we have the lemma. So this basically says that we pick a subset of Z, subset A of Z, and we pick an element, let's call it N, and this subset is non-empty. Subset of Z plus, then A has a smallest element. So this is our lemma. We now prove this lemma. So firstly, when n is equal to 1, I think I did a typing mistake here somewhere. Yeah, I did a mistake here. So we pick n from the set of positive integers, and then we have 1 through n, and we call this A. Then A has a smallest element. Okay, so now we prove this one. So when n is equal to 1, then A is just this singleton set 1. So 1 is smallest here. Suppose this holds for suppose this holds for 1 through n. Now we will show that n plus 1 is also in A. Basically, we are proving this by induction. So now let's see be a non-empty subset of 1 through n plus 1. Now, if C is equal to n plus 1, if C is just this, then n plus 1 is the smallest element of C. And then otherwise, consider C intersection with 1 to n plus 1 this set. Now, since n is in A, this set has a smallest element. Since we assume that it holds for n. So this shows that C has a smallest element as well. So thus A is inductive because we have 1 in A and then n plus 1 in A. So A is inductive. So A is equal to Z plus. And then the statement is true. We just proved it by induction. True for all in positive integers. So that's our lemma. Now we will use the lemma to prove our theorem. So theorem proof. So let's just look at our lemma first. So it says that if we pick for every n in this in the positive integers, for every positive integer n, and this set A, that is non-empty subset of the positive integers, then this subset has a smallest element. This subset that has 1 through n. It's like a finite set, not necessarily the entire C plus. So now we prove the theorem that every non-empty subset of Z plus has a smallest element. So now let D be a non-empty subset of Z of C plus. Now pick any n in D, then the set A equals to T intersect 1 through n is non-empty. So this set A is non-empty here. So A has the smallest element. Let's call it M. And this is we just arrived at this fact by the lemma, by the previous lemma we proved, by preceding lemma. So therefore, M is the smallest element of D. So we are done with this proof now. So we have proved the well ordering principle. We said that every non-empty subset of these positive integers has a smallest element. Then we used a lemma to help us prove. Lemmas are basically helpers. So the lemma said that if we take any positive integer n and this set 1 through n and call it a, if this set is non-empty, then this set has a smallest element. So we proved it by induction. We assumed it's true for n equals to 1. Then we assumed it's true for n. Then we showed that it's true for n plus 1. So that's the well ordering principle. And the final proof we have today is the strong induction principle. Strong induction principle. So this states that let A be a set of positive integers. Let A be a set of positive integers. Suppose for each positive integer n, if the section Sn, remember what's the section. So a section of positive integers is defined like this. It's basically the set of all numbers that less than, let's say, in here we have S sub n plus 1. So we go from 1 to n. So basically a set of all numbers, all integers that are less than n. So if Sn, which is the subset of this set, then n is this set, which means, actually I should say, if implies, if this statement implies that n belongs to A, then A is equal to Z plus. So here's the proof of this. So basically what it says that if you have some positive integer n and the set of some positive integers Sn, if you have all numbers that are less than n, that is contained in A, and if that implies that n is in A, then this means that A is equal to the set of positive integers. So it's kind of like induction, but you're not assuming the base case here. You're just assuming it's true for n right away. So here's the proof. So we can prove this by contradiction. Assume A is not equal to C plus. A equals Z plus just means that A is inductive. That's the principle of induction. So let n be the smallest positive integer. That is not in A. Let n be the smallest positive integer that is not in A. Then, since we have this section, every positive integer less than a is in A. Since we just said this is a subset of A, now we just said that every positive integer less than A is in A, and we claimed that n is the smallest positive integer that is not in A. So this is a contradiction to our assumption, because see here, we said suppose for each n if Sn implies that n is in A, then A is equal to the set of positive integers. So we assumed A is not equal to the set of positive integers, but then we stumbled upon a contradiction here, because every positive integer less than n is in A. N is in A. Integers that are less than A is in A, but it contradicts the fact that if Sn is contained in A, this implies n is in A. So this contradicts this fact, because Sn means the set of is the section of integers that means the all integers that are less than n. So this contradicts our hypothesis. So contradict. So here we can say our hypothesis implies that n belongs to A, contrary to assumption. So we are done with that proof now. And now I think we are finished with all of this. So that was a strong induction principle. We stated that if you have a section of integers that is a subset of a non-empty set A, and if that implies n is in A, then A is inductive. So that's the Euler ring principles, and guys, that's everything about integers from the book I've covered today. Now let me just quickly recap what we went over. So we went over equivalence relations, and then ordered relation. Then we went over the least upper bounds, greatest lower bounds, supremum and infimum. Then we went to the least upper bound property, the greatest lower bound property. Then we proved some important theorems about them. Then we started with the binary operation definition and the field definition. We defined what an ordered field is, and we said R is an ordered field with extra properties. We proved a theorem about fields, that is 0 times any number is 0. Then we defined inductive sets, and using that definition we defined the set of positive integers. We proved the well-ordered principle, then we proved the strong induction principle. I hope you all enjoyed through the end. Thanks for watching. Thanks for staying till the lecture. If there's any questions anyone wants to ask, feel free to. Okay, Albert, what's your question?
Uh, okay, thank you for
Okay, I think Zyphan is in this now.
All right. Yep. Thank you, everyone. Same.
Thank you, by the way.